I'm going to try and make this kind of short. We'll see how I do. This is on boilers. Boilers is covered in chapter 7 of your book. Here we have the PowerPoint for it. I've got the book queued up over on another page. We'll see that. Again, this PowerPoint was made available to me by Miss LaRue. Her PowerPoint follows along fairly well. It's got some information on what the different types of boilers are. And I don't know that that's really all that important here as far as getting to the statistics of what they are. I like how she lists here that the fire tube boiler has tubes containing flame are surrounded by water compared to a water tube boiler which has water in the tubes, which is surrounded by flame. And then finally they have the fluidized bed boilers, which is more common these days. I found a very nice YouTube video that I want to make reference to it's already in the assignment page. Again, the page numbers are listed here to show you just how those boilers are. I'm going to show right here, this is the fluidized version right here. And what happens is we're going to blow air in here, and that air is going to make this sand or limestone, it'll look like it actually boils. It'll look like it's liquid. And that'll be a good way to put the fuel on top of it so that it's continually moved around, and it allows the ash to be pulled away as it burns off. So it's a pretty neat thing. Again, I mentioned to you that I've got a YouTube video right here, right? So here, I found these. They're very nice here. And so I want to suggest that each of you watch this. This is only a 2-minute version, and here's a almost 4-minute version. So these are things that will be worth watching. One thing that neither of these show or discuss very much is just how do we remove the ashes? How do we remove the ashes? Are they all blown up and away? It's quite possible that this is how this works. I would expect that periodically a clean out would be required. So again, I want you to have a look at those videos. That'll be very helpful. This is an example of a boiler that was found in the PowerPoint here. And again, we can see, just how it's got the fire tubes here, right? And then the water passes through this way. You can see this is a pretty large device. There's quite a bit of controls to it. We can see there's an electric motor for pumping. We have to pipe in the gas, which is the fuel. We have to do some filtration of the gas and so forth. So there's quite a bit to this. The purpose of this class is not really to teach you how a boiler works, but just to get you comfortable and familiar with how they look. Great example here of just how it works. This is one would be a water tube type where the water passes through it. We're going to see how it's going to rise to the top, and then we're going to be making steam here. The water inlet is going to be having the return water, sometimes called condensate, okay? And that's going to come back in here. And notice the flue, notice this flue, which is allowing the burnt gases to leave, is also going to be surrounding the water inlet. So we're going to be preheating the condensate to get it back up to temperature. When it comes back into the tank, the cooler stuff will settle to the bottom to be reheated and recirculated around. It's kind of neat. Okay, this is a standard type boiler that you may find in a home or in a small apartment or office complex, and we can see all the different components that are listed here. Again, it's not. I really don't think the purpose of this class is to teach you very much about boilers, other than the main flow of it and how it works in with a steam distribution system. So. Things we're going to have to monitor, obviously, the flame, the temperature, the low water. If the boiler runs out of water, we want to make sure that we shut the thing down, because if you don't, you will blow a hole in the tubes, and that's going to be costly a repair. We're also going to have to monitor gas pressure, both high and low. Something that's not listed here is the outside temperature, right? What's the temperature outside? The reason we need to know that is to know how much pressure is being exerted on the building. If it's 20 below zero out, we know that we're going to want this boiler performing quite strongly. If it's not 20 below, if it's 50 degrees out like it is today, then the boiler may still have to run, but it may not have to run as hard. And so we can temper that as an energy savings measure. Fuels. This is actually pretty good, and there are some good examples here. If you see Table 7-3, there's a really nice example on comparing the different types of boilers, whether it's in this case here, we're going to see coal or fuel oil or natural gas, but we can also have some unconventional things such as a waste stream. And what waste stream would that be? Well, I guess it depends upon where you're at. If you're in Georgia, where they make peanuts, where peanuts are grown and packaged, quite often you may have a whole lot of peanut hulls, and those peanut hulls could be used. And so you'd be able to determine what the BTU ratings are for that particular waste stream, so you can determine how much you need to figure out if you have a reliable source of this waste stream. It's all well and good to put in a waste stream boiler, but if you don't have the waste on hand, then you'll be trucking it in from other places, and that may be more difficult than just opening up a natural gas line. So the comparisons are listed here on page 294 and 297. I really like this drawing. Unfortunately, you can't really see what it looks like on this picture here. Let's see if we can find it in the textbook. I'm looking at this particular version of the textbook. I don't think we have the same image that she's got. We have one on page, well, let's find it. Oh, let's try, there we go. Since I'm here, one of the things I do want to talk about is when we do the analysis of the coal. Different fuels are going to have different contents. And we know that when we burn the coal is going to create an ash. So depending upon how much the type of coal it is will determine how much of that ash is going to be left over and then therefore need to be hauled away. Okay. And notice it's saying here that high heating value indicates the amount of heat necessary to heat and vaporize all the water in the coal. And we see the low heating value. Okay. If the heat is subtracted, if we've already taken out the moisture that's in it, then we end up with a low heating value. All right. All right, so again, we're looking for, there's a comparison of the fuels, and so we can see just how much sulfur and hydrogen, carbon, and oxygen, moisture, and ash would be resulted from them. And the references are located in the back of the chapter. This is the cost comparison. We'll look at that in a minute. What I want to get to is this drawing. All right, this is a really interesting drawing, and it's available to actually do the math. So this is the boiler. The boiler itself has really just a few inputs, right? Okay, one of the inputs would be the coal or whatever the fuel is, and they're showing how many tons a day, right? And based on the content of it will determine what the BTU per pound is. So you're going to have to take the tons and multiply it times 2,000 and then multiply it times the amount of BTU per pound to determine just how much energy is coming in. So what else is coming in? Well, we're going to need to bring some makeup water in, right? And that makeup water is going to come in at a tempered 80 degrees Fahrenheit. Okay, so if it was coming straight out of the ground or straight out of the water treatment facility, it might be a much cooler level here, but we're going to use other equipment to raise that temperature up so that we can not lower the efficiency of the boiler. So what else is going to be coming in? We have to have combustion air. That too is going to be raised in at 80 degrees Fahrenheit. If we can control that, we'll have a better control on the system. So notice the reason we're picking combustion air as 80 degrees Fahrenheit is because the ambient conditions around the boiler are 80 degrees. Around the flue itself is 50 degrees Fahrenheit today. What's it going to be on January 3rd? Maybe it'll be 20 below. So we need to consider those sorts of things as well. So the last input to this we saw in the earlier picture was the condensate return. So let's see what that is. So what that is, this is after the steam or hot water leaves the boiler, right? The steam is leaving at 8,000 pounds per, I'm sorry, 85,000 pounds per hour at 250 psi. That's atmosphere. Okay, so after it goes and does the work that it's going to do, which we'll read about in the next chapter, it needs to be returned then to the boiler to reabsorb the energy. So that's what happens. We're going to absorb the heat from the burning coal into the steam, and then the steam will be delivered to the load, whether that's a radiator in a room or a piece of process equipment, or it could be a variety of things. And so that energy that's contained in the steam will be then released into the load. And once that temperature gets low enough, the steam then, of course, turns back into water. Well, it'll still be pretty hot water, right? But if it gets too much lower than 150 degrees, imagine what's going to happen when we dump colder water into this boiler, right? So we're gonna lose some energy here. So those are the inputs to it. Okay, so again, we have coal, the fuel, air, the makeup water, because we have to make up for what gets lost out there doing the work. Sometimes this will happen, and it's calculatable. So now we have to take a look at what goes out of the boiler. Well, the first thing that goes out is the steam. That's the most important thing. We want the steam to go out and do the work. Well, the heated gas, right? Once the gas is burned, that has to be exhausted. And so it's going to be exhausted up the flue, the smokestack, if you will. Okay, and they're showing that that flue has a surface area of 450 square feet. You could calculate that the same way you'd calculate the surface area of a cylinder, or maybe it's more than likely round. Okay, and we can see what that temperature is, but we can also see that it's in 50-degree ambient air. So that's the surface loss. Well, we're also losing the actual gas, right? So the gas itself that's going up the chimney or the flue will have a temperature, and we will know how fast it's moving. In this case, 33,200 cubic feet per minute, which could then be calculated to be 77,060 pounds per hour. So we have to calculate all of those things. Other ways we're going to lose heat. The boiler itself has a surface area. Now we can insulate it, and we will, so we can keep most of that heat in, but we'll lose some. Insulation isn't perfect, and then periodically we have to do this thing called a boiler blowdown. Now there's two ways to do a boiler blowdown. There's a bottom boiler blowdown and a top boiler blowdown. When we blow down from the bottom, we're getting rid of sludge and slag and stuff that has residue that didn't go up the flue with the gas, but instead sunk to the bottom. So we need to get that junk out of there for two reasons. One, it's corrosive, and two, it'll end up blocking some of my passages. So we're going to lose some heat when we dump that 400-degree water out. All right, so we have to calculate for all of that. And it's actually discussed on these pages, right? It tells exactly how to do this. And the math is actually pretty straightforward. What you have to realize, though, is that the temperatures we're listing here are for this R, temperature degrees in R, that's going to be Rankine, okay? Okay, that's the Rankine temperature. All right, so those numbers are all covered on the next page, and they were also covered on the page before. Now, in calculating for these losses, you'll notice that the author, he's pretty liberal with his rounding. And so when I do the math on my calculator, my numbers come out to be a bit different than what he comes out with. Even the ones that are shown right here, I come up with some different numbers just because of the way we're rounding. But you guys should be able to go through and do this and make as much sense out of it as I did. I'm going to go back now a couple of pages because I want to look at this comparison. This comparison right here is described on a couple pages before, right? A couple pages before it describes this, and it gives some alternatives. All right, so here we go. This is an interesting one because this might be one that you would have to calculate. So, company is using a process steam at rates that sometimes reach as high as 300,000 pounds an hour. They currently use a gas-fired boiler that is capable of meeting its needs. Now, we've got to remember, this particular chapter was written back in the 90s when the cost of natural gas was fairly high. Right now, natural gas is one of the cheaper fuels that we can get in order for a boiler. So you may not be doing this. You may be doing calculations the opposite way. They may have a coal-fired boiler that they're getting ready to take offline, and you would need to recalculate it for using gas. Regardless of that, they're giving us different alternatives. One alternative is just keep buying gas and sending the waste to the landfill. Okay? And by the waste here, they mean the company makes waste, literally trash. So somebody has to come and haul that trash away. Well, one of the alternatives would be to install a boiler that burns that waste. Well, that was an option several years ago. Well, we're starting to see companies become more environmentally conscious, and so we will not be, hopefully we'll be doing less and less of this. But for the sake of this argument here, or this example, what follows is the alternatives here. So, and it's explained fairly well here, I think. It explains the pros and cons of doing it one way or the other way, and what the different costs are. Well, there is a question in the problem set, question 7-2, which is the answers for it are significant. They're just, and I'm not going to assign that because it's a little bit too much work. I will, however, post the answers so that you can see them. So you'll be able to see those answers, and even though it's not one of the ones I'm going to post. All right, so let's just look at the table. And we can see pretty much everything right here. So the present system, you can see that we've got the gas cost, right? The gas cost, $2.5 million a year is what we're costing. If we go this new route here where we use 2 boilers, we'll stop using gas altogether. But you'll notice in the 2 boiler scenario, one of the boilers runs on coal and the other one runs on waste. Okay, so we're going to have to do maintenance on both of them. But see, the benefit of using the 2 boiler system is we can burn as much trash as we have, right? Whatever the trash that we have, all of this trash that we're currently paying $150,000 to get rid of every year, right? We get rid of that, and now we'll still be hauling some waste and some ash, but it'll be considerably less because what we're doing is we're hauling not 40 tons, not 40,000 tons of waste, but instead 6,940 tons is what we'll be hauling. So that's a considerable drop. And the same thing with the ash. We won't be burying 40,000 tons worth of waste. We'll be burying 6,940 tons. So we'll save a lot of money there. All right. Well, but we also know that we'll have to, I don't think they calculated, yes, they did. Yes, they did. So that's all the ash. Okay, and that includes the coal ash, right? That includes the coal ash. And that's actually explained on the page before where it talks about alternative 2. And again, this is a place where my numbers didn't come out the same as theirs, right? Their numbers came out, this number here, they came out to 5,580 tons. I actually came out to be a little bit less, again, using their math. So you may, who knows, there's a good possibility I was doing it wrong. So if you guys find that his numbers are correct, then please show me where I was wrong, because I came up with 5,563. Yeah, so that's where that comes out. And then the other alternative then here is to go with get rid of coal completely and just have one great big waste boiler, right? And so you'll notice we're going to reduce, right? We're going to reduce the amount of maintenance, right? Because we'll only have one boiler that we're going to do maintenance on as compared to the 2 boiler operation. We'll no longer have any waste, but what's interesting here is, whereas, and this is what's kind of puzzling to me, is notice here we're going to have revenues, right? Revenues of $450,000 because we're going to have other companies paying us $15 a ton for their trash. That's what this says. But wait a second. Why would they pay me $15 a ton if I was getting rid of it for basically $3.75 a ton? So I don't quite understand how he comes up with these numbers as a revenue and these numbers as a cost. And it could just be because of the volume of trash that I have that may, so the other issue with this particular example is that what happens if I run out of trash? What if people stop paying it? What if they find somebody comes in and says, hey, we'll do your trash for $10 a ton? Then what? Now how am I going to get it here? Okay, I need the trash or I don't make the steam. So there's some issues with both of these. So that's the scenario with that. All right. Let's go back to Helena's PowerPoint here, see what I missed. Okay, so the heat balance tool, we kind of went through that a little bit already. It goes through a little bit further in the text. And so these are the steps required. We're going to calculate the heat gains on the inputs and the heat losses, and we're going to sum the thing up and see what kind of energy will be needed to make up the difference. We'll have to do things, we want to consider how we can make the boiler run more efficiently. Some ways that aren't improved here, well, it actually tells us by changing the oxygen content, we're going to be able to change the efficiency of it. I don't know if you've ever seen a chimney that's got really black smoke coming out of it. Okay, that means it doesn't have enough oxygen going into it. Okay, and that's because so what happens is I'm running in reduction there, and I'm lowering the efficiency, which means I have to use more fuel to get the thing to burn. So what I need to do is improve how I'm monitoring the air. So that's a big thing right there. If I can improve how I'm monitoring it, and then I can make changes to the amount of air that's in the system, I can make the thing burn far more efficiently. We also have to take care of our load management, make sure we're not wasting energy through inefficient loads or leaks that are listed here also on this sheet. We have to treat the water. There's a big, huge problem right here because the water that gets put back into the boiler, if it has a very high oxygen content, that turns to rust, especially when it gets hotter. So we have to find a way to what's called de-aerate, right? De-aerate. And so that process is a very important thing that you will be spending time and money on. So that's boilers. Let me go back to the textbook and see if I skipped anything else. Let's come along here. There's the gains. Here we're doing the balancing. You guys can do this math here in the book just as well as I can. There's a really neat chart coming up here, figure 7-11, I believe. All right, figure 7-11, I kind of like that. This is another chart here that's kind of interesting because notice we're looking at the properties of saturated steam and water, and this is a property of the pressurized, right? So this is pressurized steam, right? Saturated water, as compared to the next chart where we're going to be talking about temperature, okay? So if the numbers are a little bit different on these charts, just a little bit. And what you can look at is what I ended up doing is going through the table and finding the numbers that we were using in the calculations. For example, at one point we were looking for the 250-pound steam and how much energy it had, and it turned out one of the numbers we were looking at was this one right here, just as a hint for when you're trying to go through and look at the numbers. Okay, and that's a hint. But if we compare that, right, this is the 400-degree temperature here, that's the value it has. But if I want to see what the enthalpy, right, the enthalpy is of the saturated liquid, all right, so we're going to go over onto the next page, and we're going to find, well, here's the 1201 here, right, but also this is the actual temperature of it, 375. Whoops, too much, just right here, okay. So we're going to highlight that, and notice here we're using that same 1201 degrees. Okay. So hopefully you guys have read through this already. Again, there's the chart, and as you go through this, I want to challenge you guys to figure out where the flue gas comes from. Okay, where in the heck does this number come from? We got different numbers that are listed in the writing before and after this page. See if you can figure out where that 16,150,000 BTUs per hour comes from. Pretty interesting. All right, we already looked at the efficiencies of it, and this is the chart. I really like this little chart, and it explains it fairly well, just how we would do this. And so depending upon the amount of oxygen, right? If the higher the oxygen content, look what happens to the efficiency of this thing. If I can get a lower oxygen content, right? And notice I'm going to run this over to the temperature it's running at, right? So I knew our output temperature was going to be 450 degrees, and we can see the slope of this, right? So at 9% oxygen, I can see my combustion efficiency is about 76 point, I don't know, maybe 76.5, something like that, right? But if I lower the oxygen, right, if I get that oxygen down to 2%, I just follow this slope up here, this 450 degree slope to where they intersect, wow, my efficiency got up to 82%. Even that's terrible. And so what we're doing is we're looking at the temperature of the flue right here, right? If I can get that flue lowered, flue temperature lowered. All right. So that's what that's about. All right, so that's pretty much it here on this chapter on boilers. I'm going to stop this video and start a new one on the steam distribution systems here momentarily.